Hello, my name is Nils Nilsson. I helped in the development of A-Star and STRIPS. I'd like to explain a little bit about the history of those programs. In the mid-1960s at SRI, then called the Stanford Research Institute, I was working on a robot called Shaky. Shaky had several programs, some for dealing with perception. We had machine vision programs, for example, and some controlled Shaky's actions as it moved around in its environment. There were two problems in developing these programs for controlling Shaky's actions. One problem was how Shaky should navigate throughout a room strewn with obstacles without bumping into any of them. Another problem concerned how Shaky should put together its high-level actions in order to achieve high-level goals. With regard to the navigation problem, we set up waypoints that were adjacent to and somewhat standing off of various obstacles in the room. These waypoints could be considered nodes in a graph. The edges of the graph would be the straight line distances between waypoints that Shaky would be able to travel. So the problem of navigating from one point in the room to another is the same as the problem of finding the shortest path in a graph. Edgar Dijkstra had an algorithm for doing just that. But the problem with the Dijkstra algorithm was that it searched outward from the start node toward the goal in all directions. What we wanted was an algorithm that focused its search more in the direction of the goal. Now, I was aware of a program developed at Edinburgh University, the Graph Traverser program by Jim Doran and Donald Mickey, that did focus toward the goal. Their algorithm assigned numbers to nodes in the graph that were purported to be the difficulty of achieving the goal from that particular node. I suggested that that number ought to be an estimate of the distance from the node to the goal, ignoring any obstacles that might be in the way. A colleague at SRI, Bert Raffel, suggested that the number ought to involve also the distance from the start node to the node in question, and that would prevent Shaky from being led down promising but ultimately futile paths. Another colleague, Peter Hart, suggested that if the estimate from a node to the goal was a lower bound on the true distance Shaky would have to travel from that node to the goal, then the algorithm, which we named A-Star, would in fact achieve the shortest path that was possible. Then Peter Hart and Bert Raphael and I together set about to prove Peter's conjecture, and that was the development of the A-Star algorithm, which involved this number associated with each node that was a sum of the distance from the start node to the node in question, plus the estimate of the distance from that node to the goal. With regard to the second problem, the one of stringing together Shaky's higher level actions to achieve high-level goals, Richard Fikes and I, another colleague at SRI, developed a system we called STRIPS, for Stanford Research Institute Problem Solver. STRIPS used high-level models of Shaky's world. That is, instead of just the coordinates of positions in Shaky's room, we used a database of facts that were true of particular situations that Shaky could get itself into. So we still wanted to be able to solve the problem of achieving these high-level goals by some kind of graph searching program. And so the starting node of the graph would be a list of all the facts that were true in Shaky's present situation. The goal then was also described by some statements of facts that we wanted Shaky to make true by applying actually these high-level actions. So what we needed in order to convert this into a search problem in the graph would be a computational way of producing states of the world, that is, other databases describing what a particular state of the world would be when Shaky applied one of its high-level actions. To perform that computation, we invented something called STRIPS rules. Now, a STRIPS rule would consist of a precondition, that is to say, all the facts that had to be true in a particular world in order for Shaky to apply one of its high-level actions, a delete list, that is to say, a list of facts which could no longer be guaranteed to be true if Shaky did apply one of its high-level actions, and an add list, which would be those facts which the high-level action would make true. And so what we did is use these strips rules to go from one state, that is one database describing Shaky's current situation, to successor states in the graph. So we could even use the A-star algorithm if we had a good way of estimating what the distance would be from one of these databases to one which had Shaky's goal achieved. So we could use A-star if we had that particular system. Actually, in the system that we employed and programmed, the strip system, we worked backwards from the goal by applying these strips operators in a somewhat backward direction. Those of us who were involved in the development of A-star and strips are gratified now to know that these systems are used in many present-day AI applications.